Hello everyone, this is Kalpana here. In this video, we are going to solve a differential equation using variation of parameters method. So let's get going. Problem: solve y double dash plus y equal to secant x cosecant x or d square plus 1 into y equal to secant x cosecant x using variation of parameters method. We are given a differential equation of order 2. Given differential equation, y double dash plus y equal to secant x cosecant x, considered as equation 1. Now write y double dash as d square y by dx square plus y equal to secant x cosecant x. We can write d square y by dx square as capital D square y plus y equal to secant x cosecant x. Now take y common from these two terms. We'll get d square plus 1 into y equal to secant x cosecant x, considered as equation number 2, which is in operator form. Equation 1 in operator form is equation 2. Say f of d into y equal to some function of x, where f of d is d square plus 1 and r of x is secant x cosecant x. Right? Now we'll find the solution to equation 1 and 2 using y equal to yc plus yp. Okay, the general solution to 1 and 2 is given by y equal to yc plus yp, and we'll get yc using the auxiliary equation, and later using yc we'll write yp and we'll use some formulae. Now coming to the auxiliary equation, the auxiliary equation is f of m equal to 0, where f of m equal to, we have f of d square plus 1, right? Let's replace differential operator with m so that we'll get f of m equal to m square plus 1. Then the auxiliary equation becomes m square plus 1 equals to 0. Now we need to find roots to this equation. M square equals to minus 1, then m equal to plus or minus square root of minus 1, which gives us plus or minus I, since square root of minus 1 is I. Therefore, m equal to plus or minus I. The roots are complex conjugate. We know that when m equal to a plus or minus ib, that is the roots are complex conjugate, then yc or complementary function looks like e power ax into c1 cos bx plus c2 sin bx. In case of a0, we'll get e power 0 into x, which is e power 0 of c1 cos bx plus c2 sin bx. Since e power 0 is 1, so we'll get 1 into c1 cos bx plus c2 sin bx, which gives us c1 cos bx plus c2 sin bx. Right? Let's now write the complementary function to our problem. Yc equals to, now compare plus or minus I with plus or minus ib, then for b equal to 1 we'll have yc equals to c1 cos 1x plus c2 sin 1x. which gives us c1 cos x plus c2 sin x, or therefore yc equals to c1 cos x plus c2 sin x. We got yc. Let's now find yp. Just replace the constants or parameters with some functions of x. Let yp equal to, replace the constants c1, c2 or parameters with functions of x, a and b. Then we'll get yp equal to a cos x plus b sin x. Yp is nothing but particular integral, okay, where a and b are functions of x. Now we can compare yp with au plus bv, or yc with c1u plus c2v to find u and v, where u is cos x and v is sin x. See, u is cos x and v is sin x. Now we'll find a and b using formulae. A is given by integral minus v into r of x by uv1 minus vu1 into dx, and b is given by integral u into r of x by uv1 minus vu1 into dx. Now let's find uv1 minus vu1 firstly, because it appears in both the formulae, right? And later we'll go for a, b, yp, and finally the general solution using y equal to yc plus yp. v1 is nothing but derivative of v with respect to x, minus v into u1 is nothing but derivative of u with respect to x. This is equals to u cos x into derivative of sin x with respect to x minus v sin x into derivative of u, that is cos x with respect to x. This gives us cos x into derivative of sin x with respect to x is cos x minus sin x into derivative of cos x with respect to x is minus sin x. This gives us cos x into cos x is cos square x, minus into minus plus sin x into sin x is sin square x, which gives us, or we can write it as sin square x plus cos square x, since sin square theta plus cos square theta equal to 1. So from this we'll get sin square x plus cos square x equals to 1. Therefore uv1 minus v1 equal to 1. A is given by integral minus v into r of x by uv1 minus v1 into dx, right? This gives us, just substitute the values, or v r of x uv1 minus v1. We'll just get minus v is sin x into r of x is secant x cosecant x by uv1 minus v1 1 into dx. This gives us minus integral sin x secant x into cosecant x dx. Since cosecant x is reciprocal of sin x, so let's replace cosecant x in the next step. Okay, cancel sin x, we'll get minus secant x dx, minus integral secant x dx, since integral secant theta d theta equal to log mod secant theta plus tan theta, right? So this gives us minus log mod secant x plus tan x or minus log of secant x plus tan x. Therefore, a equal to minus log of secant x plus tan x, right? Now let's find b. B is given by integral u into r of x by u v1 minus v1 into dx. This is equals to u cos x, r of x is secant x, cosecant x by u v1 minus v1 1 into dx. This gives us integral cos x, secant x, cosecant x into dx. Since secant x is reciprocal of cos x, so let's replace secant x now with 1 by cos x into cosecant x dx. Cos x gets cancelled, we'll get b equal to integral cosecant x dx. Since we know that integral cosecant theta d theta equal to log mod cosecant theta minus cos theta, cot theta. So we'll get b equal to log mod cosecant theta minus cot theta or log of cosecant x, it's x, right, not theta, cosecant x minus cot x. Therefore b equal to log of cosecant x minus cot x. We got a and b. Let's now find yp. Yp is given by a cos x plus b sin x, right? Where a is minus log of secant x plus tan x into cos x plus b log of cosecant x minus cot x into sin x. This gives us minus cos x log of secant x plus tan x plus sin x log of cosecant x minus cot x, which is our required yp. We got yp and already we have yc. So let's now write the general solution using y equal to yc plus yp. Therefore, the general solution is given by y equal to yc plus yp. Then y equal to c1 cos x plus c2 sin x plus yp minus cos x log of secant x plus tan x plus sin x log of cosecant x minus cot x. This completes the problem. So this is all for now. I hope you'll understand. We'll see you in the next video. Until then, bye bye.